For us in the math world, the really great transcendent hero of infinity is Georg Cantor. Cantor lived in the mid-1800s and came up with ideas that are so mind-blowing and so stunning that we're still kind of reverberating from his insights. The biggest of all is that there are different kinds of infinity. Some infinities can actually be bigger than others. And the way we'll do this is with a charming video that was produced by the Open University a couple of years ago.
60-second adventures in thought. Number 4, Hilbert's Infinite Hotel. A grand hotel with an infinite number of rooms, and an infinite number of guests in those rooms. That was the idea of German mathematician David Hilbert, friend of Albert Einstein and enemy of chambermaids the world over. To challenge our ideas about infinity, he asked what happens if someone new comes along looking for a place to stay. Hilbert's answer is to make each guest shift along one room. The guest in room 1 moves to room 2 and so on. So the new guest would have a space in room 1, and the guest book would have an infinite number of complaints. But what about when a coach containing an infinite number of new guests pulls up? Surely he can't accommodate all of them. Hilbert frees up an infinite number of rooms by asking the guests to move to the room number which is double their current one, leaving the infinitely many odd numbers free. Easy for the guest in room 1, not so easy for the man in room 8,600,597. Hilbert's paradox has fascinated mathematicians, physicists and philosophers, even theologians. And they all agree you should get down early for breakfast.
So the question starts to become, well, if infinity is really that big at the Hilbert Hotel, is there any number of guests that you couldn't accommodate at the hotel? I mean, are there infinities so big that even the Hilbert Hotel would not fit them? And so Cantor worried about this and came up with an attempt to find an infinity too big even for, I mean, he didn't think in terms of the Hilbert Hotel, but let me illustrate it that way by imagining a situation that if you're kind of a nasty contrarian, you might think, what if an infinite number of buses, each carrying an infinite number of people, show up? What will the night manager do with this? And so here's the solution to it. Let's first visualize these people by showing a picture which will have a row containing all the infinitely many guests that would correspond to bus number 1, and then there's bus number 2, each with its infinite number of guests, which I'm going to depict as faces. And then there's an infinite number of these buses. So there's the first image. It's not supposed to just be 4 by 4. You're supposed to picture it with infinitely many guests in each row and infinitely many buses. All right, now, a first inexperienced manager might attempt to solve the problem this way. I mean, what the goal is to assign each passenger a room. And the problem will be solved if, for any given passenger, you can say, that person is in a room with a finite number, a specific number. Like, imagine a guest list, and I can say, oh yes, Mr. Smith, you're going to be in room 133. As long as everybody has a room, everybody's happy. Here's the first attempt to put people into rooms. Let me put person 1 from bus 1 in room 1. And then I'll put the second person from that same bus in room 2 and the third person in room 3. You can see this is not a good solution. Do you see what the problem is? No one in bus 2 is going to be happy. Because the whole hotel will be filled just with the passengers from bus 1, and so you'll have infinitely many busloads of infinitely many unhappy people. This is not what you want at your hotel. So that is not a good solution to the problem, but there's a much more clever way of doing it, which then does actually accommodate everyone. What you do, notice this zigzagging pattern of arrows. You start with the first person, that person gets room 1. The second person is at the end of the first arrow. So that would be passenger 2 in bus 1. Then you go down to bus 2, passenger 1, that person gets room 3. Just follow the arrows, and that's the order in which people are placed into rooms. Can you sort of see what's happening, how it's fanning out from the corner? And that will have the property that you can pick any person in that infinite array, and that person will be served in a finite time. They will have a room. So this is a way of actually accommodating infinitely many people in infinitely many buses in the Hilbert Hotel. This raises the, oh, by the way, I should say that there's the abstract version of this, which is that this shows that the fractions, the positive fractions, any fraction you can think of would correspond to one of these passengers, like the person in bus 4 and passenger 17, that might be what we would call 4/17. I mean, there's a correspondence between the people in these diagrams and the positive fractions. And so this argument that I've given you here is essentially Cantor's argument for showing that the positive fractions can be counted in the sense that they can be put into what Cantor called a one-to-one correspondence with the natural counting numbers, the numbers 1, 2, 3, 4. That is, there's a way of listing all positive fractions so that we can say this is the first one, this is the second one, this is the third one, and every positive fraction will be at some finite place in that list. They're not ordered by size, by the way. They're ordered in this way that I just described with this zigzagging pattern. So the rational numbers, the fractions, are countable, meaning they can be put into one-to-one correspondence with the natural numbers, 1, 2, 3, 4, and so on. And this raised the question in Cantor's mind. It seems like everything he could think of is countable. Every infinity he could think of was countable, or to put it another way, the Hilbert Hotel really lives up to its motto. There's always room at the Hilbert Hotel. Well, actually, though, in 1873, Cantor discovered an amazing example showing that that was not true, that there's an infinity that is so big that it would defeat the Hilbert Hotel, no matter how clever the manager is. And this has to do with the amount of infinity contained in a continuous line. If you imagine the number line, you know, the traditional number line that was tacked on the wall of your elementary school, and it shows the integers 1, 2, 3, 4, and there's all the space in between where all the fractions are and all the irrational numbers. That continuous line, what we think of as the real numbers, if the real numbers showed up at the hotel, there wouldn't be room for all of them. And here's the proof. This is Cantor's famous diagonal proof. He said, imagine that there was a roster, a sort of a guest list, and this was a guest list. It's going to be a proof by contradiction. I'll show that there's a real number that doesn't have a room. Here's a putative list where room 1 is assigned to this real number that's being shown here, 0.42, et cetera. And room 2 is assigned to some other real number. Don't worry about the details of the number. The idea is just imagine that there was a list of all the real numbers, just like we could list all the rational numbers. Maybe we could list all the real numbers. Well, Cantor's argument is no, because if there were such a list, and here's an attempt to show what it might look like, you then circle the first digit of the first number, and then you circle the second digit of the second number, 2, and the third digit of the third number, 1. So from that, you construct a real number, which in this case would be 0.421, and so on. That's not the problem. That's not the bad number. What we then do is change each of those digits in that number. Like the 4 that begins this number, maybe make it a 3, or just whatever you want. Just change it. Or the 2, that's the second digit, make it something else. Make it a 7. Just have some system. But the rule is you construct this number down the diagonal, and then you systematically change its nth digit to something else. That is, if it's the nth number, its nth digit gets changed. And so by doing that, Cantor constructs a number which is not in the list, because it can't be the first number in the list because it differs from the first number in the first place. It's not the second number in the list because it differs from the second number in the second place, and so on. So by systematically going down the diagonal and then changing every digit, he has now produced a number that is not on the list. And this argument shows that, in fact, the real numbers cannot be counted. There is no list that can embrace them all. And so with that comes the question then, this very nagging question that we're going to be talking about next, which is, well, if there are now two kinds of infinity, the countable kind and this continuous kind, which is bigger, are there other infinities? And really more to the point, is there some infinity that's sandwiched in between them? Is there some infinity smaller than the continuous infinity but bigger than the infinity of the 1, 2, 3 variety? That's called the continuum hypothesis, the idea that there is no such infinity in between. It was Cantor's great conjecture, but he never proved it.
Reach their destination and
How do you feel?
this epic journey, it all happens in about
Would you like for
a
everybody to
second.
join in?